Alright, so in this chapter we're gonna learn about ceramic materials and how is the structure of ceramic materials different than metallic materials, and what type of defects exist in ceramic materials and compared to metals, how they are different, and what are the impurities that we observe in a ceramic crystal structure. And we will look at phase diagram of ceramics, and then we're going to take a look at the mechanical properties of ceramics, how we measure them and how different they are from the metallic materials. So ceramic materials we briefly mentioned in chapter 1. They are inorganic materials. They are compounds between metallic and non-metallic elements. So when we say compounds, certain ratio exists between the reacting elements. So interatomic bonds can be ionic and covalent bonds, and we have discussed about that also. And percentage of ionic character increases with difference in electronegativity of atoms. So as you can see in the table, the periodic table, where it shows us the electronegativity of different atoms, and you can see some ceramic materials can have a larger degree of ionic character. If you look at the differences between the electronegativity of the reacting atoms, like calcium fluorine, for example, and you are seeing calcium is 1 and fluorine is 4. There is also possibility that this electronegativity between reacting elements might be small, such as silicon carbide. So for ceramic materials, when the bonding is mainly ionic, then the crystal structure might be thought as composed of electrically charged ions instead of atoms, like positively charged and negatively charged. So metallic ions that are positively charged called cations, and negatively charged ions are the non-metallic ions, which are called anions. And two characteristics of ions in ceramic materials influence the crystal structure. The first one is the magnitude of the electrical charge on each component ions, and the second one is relative sizes of cations and anions. So for the overall crystal, the crystal must be neutral. So all the cation positive charges must be balanced by an equal number of anion negative charges. And the chemical formula of the compound will indicate you the ratio of cations to anions. And the composition should achieve this balance. For example, calcium fluoride, right? And calcium charged 2 plus and fluorine charged negative. So that tells you each calcium ion has a charge plus 2, and each fluorine ion has a single negative charge. Therefore, to be in balance, we have 2 fluorine reacting with 1 calcium ion. So for oxide structures, oxygen anion larger than metallic cations. Closed packed oxygen in a lattice. This is usually an FCC structure. And the cations fit into interstitial sites among oxygen ions. and we're gonna take a look at more these in detail. Here you are seeing the factors that I told you affecting the sizes of the ions, relative sizes of the ions, and then to maintain charge neutrality, the chemical composition indicates that. And we have seen calcium fluoride, and net charge should be 0, as indicated here, and it is reflected in the chemical formula as I explained. So the second thing that is determining the crystal structure, it was relative sizes, and these are the ionic radii of cations. You can represent with RC, and atomic ionic radii of the anions. Because metallic elements give up the electrons when ionized, cations are smaller than anions. So therefore, RC over RA is smaller than unity. Therefore, that explains when oxide structures, meaning a metallic ion reacting with an oxygen anion, oxygen anions taking the electrons, they are larger than the cations who are giving up their electrons. Each cation, the positively charged ions, they will try to prefer to have as many nearest neighbor anions as possible. And the anions also desire a maximum number of cation nearest neighbors, because this packing makes the structure possible and more stable. Stable ceramic structures form when those anions surrounding a cation are all in contact with that cation, such as this one, that one, but not this one. The coordination number, that is the number of anion nearest neighbors for a cation, is related to cation to anion radius ratio. For a specific coordination number, there is a critical or minimum RC over RA ratio for which this cation and anion contact is established. So if we take a look at the coordination numbers and the ratio, RC over RA ratios, for ratios less than 0.155, there is a very small, you see, cation that is bonded to two anions in a linear manner, and this of course have a coordination number of 2, and when the coordination number is 3, and this is the type of packing here, so this means that each cation is surrounded by 3 anions in the form of a triangle, and the cation located in the center. The coordination number is 3, as I said. The ratio is in between 0.155 to 0.225. So you see the amount of neighbors is affected by this ratio, the sizes, atomic radii, ionic radii. For the coordination number 4, The ratio is in between 0.225 to 0.414. The cation is located at the center of a tetrahedron, like this one. Okay, so we are looking from top. The cation is actually at the center, and the anions are at each of the four corners. When the ratio of atomic radii, cation to anion, is in between 0.414 to 0.732, so there is 6 anions, one each. It's a form of octahedron. It's a form of an octahedron, and the cation is at the center of the octahedron and surrounded by 6 anions, all of which are at the corners. And you can see from an up view here, right? So there is gonna be 6, 1, 2, 3, 4, 5 in the bottom, and 6 on towards us, and in the middle there is the cation. Okay, so for the coordination number 8, when atomic radii, ionic radii ratios are in between 0.732 to 1, in this one the ions at all corners of a cube and a cation position at the center. And you should look at your book because they have colorful images in that. So this is black and white, so you can also visualize better. The most common coordination numbers for ceramics: 4, 6, and 8. So we then say the coordination number increases with increasing ionic radii ratio. And you can see how different crystal structures of different ceramics, like zinc blende, sodium chloride, cesium chloride, these are all having different number of coordination numbers and different ratio, the ionic radii ratios, and based on that the crystal structure is determined. So it all depends on the sizes of cations and anions and their relationship, and that's how the structure is determined for ceramics. Let's now see how to determine how these ratios are determined. So the ratio of the atomic ionic radii of cation to the ionic radii of the anion. So for an octahedral site, meaning the coordination number is 6. So this is just one example here, okay? So here we are seeing an cation in the middle, red, surrounded with anions, and we are seeing it has coordination number 6. 1, 2, 3, 4, 5 towards us and 5 towards the screen, 6 towards the screen, and in the middle there is the cation. So if we draw a square going through the centers of this, the centers of the square is in the centers of the anions, like this, and then if we draw a diagonal here, if this is a, this is a, this is a square root 2, okay, and the length of this is, of course, we know there is 2, so this is r of anion, so 2r anion, and there is the little one that is 2r cation, right? This is equal to a square root 2a. And we also know A is equal to 2r anion because of here, right? So we also know that. So that is, if you plug that information in here, so this plus that is equal to that. So just plug it in here. And if you divide each term with 2, this is what you get. And if you arrange one side as anion, the other is cation, and 2 can take the ratios, bringing this to the denominator, which is square root 2 minus 1, which is 0.414. It's right there, right? Bond hybridization happens, remember, when there is covalent bonding forming. This one example is silicon carbide. This is similar to zinc blend crystal structure. Here we are seeing, if you take a look back at the structure here, we are seeing a zinc blend where there is a tetrahedron forming, and the corners are sulfide ions, and the middle is the zinc. So the blue one is the zinc. Similar to that, silicon carbide forms the same structure. At the corners of the tetrahedron, there is carbon, and in the middle of this tetrahedron you are seeing here is the silicon. So it is the same structure. If you take a look at this, the ionic character is low, like 11.5, and that means remaining is covalent bonding. And covalent bonding happens with, remember, preferential directions. Therefore, sp3 hybridization requires silicon carbon to approach silicon at certain angles. They form tetrahedrons, and in the middle of this tetrahedron, corners are carbon. In the middle, there is the silicon. So let's take a look at an example. Here we are going to predict the crystal structure of iron oxide. So here, on the basis of ionic radii, what crystal structure would you prefer, would you predict for iron oxide? And here we are seeing that we look at the ionic radii of the iron and oxygen. Of course, we found those from tables given to us in this problem or in any kind of problem. And we find, of course, ratio is 1:1 reaction ratio, and we know oxygen is -2 charged. Therefore, to compensate the charge and reach a neutral structure, the iron should be +2 charged. And based on that, you read atomic ionic radii and then plug it into your equation ratio and calculate the ratio. And based on that, where does this number fit? 0.550. 0.550 is in between here. That means you have a coordination number of 6. A coordination number of 6 is going to give us a structure similar to sodium chloride. So we can say it's going to have a sodium chloride structure. So here the same concept is of course valid for ionic solids too. That was an example of covalent bonded structure, but a sodium chloride will have the same structure. Here, if you take a look at the atomic radii ratio, it is 0.564, which fits to the description of sodium chloride structure. And here you are seeing the chlorine anion is bigger than the sodium cation, which we explained why. And in between those packed chlorine anions, there will be octahedral sites, meaning there will be an empty regions. There will be an empty regions which will be filled with the sodium anions. So if you take a look at this, you will see the octahedron. Okay, there is the octahedron. All right, there is the octahedron right there, and octahedron in between, there is your sodium anion, sodium cation. Okay, sodium oxide, magnesium oxide and iron oxide, they also have sodium chloride structure. How is it? We take a look at the ionic radii and we take the ratio, and then we are seeing it fits in the description of octahedrons, and because it's 0.514, right? So we go back and see here it is in between. So we are forming an octahedral, and in between the octahedral we have the side, the empty side where the the cations can fit in, as I showed you here in the figure. And again here 1 2 3 4 5 6, right, 6 coordination number. It is forming an octahedron like this. And here in between those packed atoms there is the cation. In this case it is magnesium, and they both have 6 coordination numbers, which gives us the sodium chloride structure. So we are seeing here is actually different type of ceramics having different type of coordination numbers based on their ionic radii, and based on that we can predict what type of crystal structures will they have. AX type crystal structures. So some ceramic materials have equal numbers of cations and anions. Therefore they are referred as AX compounds. A denotes cation, X is the anion. And there are several different crystal structures for AX compounds. And we have seen the sodium chloride is one of them. And then we have seen zinc blende is one of them. And there is also, we have seen silicon carbide. And now we're going to take a look at cesium chloride. In this case, if we look at the ionic radii ratio of cation to anion, it is 0.9. It is less than 1, and therefore it has a cubic structure. And here you can see, remember, if you go back here, that is the ratio fits in that range, and we have a cubic structure. It is like this. So we can say whatever, if your range fits, if your ratio number fits in that range, your structure will have a cubic structure, and it's gonna look like a cesium chloride structure. And now let's go back. Okay, here. And of course in this structure the cation has 8 neighboring ions, which are the chlorine anions, which are shown with the green. And this is just the image showing us for the zinc blende. Remember, they are it's a tetrahedron structure. There is the tetrahedron here. And then AX2 structures. These are if the charges on the cation and anion are not the same. A compound it can exist with the formula here. P cannot be equal to 1 and M cannot be equal to 1. Therefore, these type of structures called AX2, like a calcium fluoride, geez, okay. And if we take a look at the atomic radii, ionic radii ratios, which is 0.8, which is according to it should have a coordination number 8. Therefore, it is the calcium ions are positioned at the center of the cubes with the fluorine ions at the corners. We can say then this crystal structure is similar to cesium chloride, like we have seen. Okay, sometimes it is possible for ceramic compounds to have more than one type of cation, such as it can have two types of cations, A and B. And this one example is barium titanide, and this is shown here. It's a complex oxide. And this is what we call perovskite crystal structure, and it has interesting properties, especially electromechanical properties that we're going to discuss later. And here you see how the structure is. We are seeing the unit cell of the perovskite crystal structure, and we are seeing that there is the octahedron forming with the oxygen anions, and then in the middle, in the octahedron position, there is a titanium anion, a cation, and then at the corners of a cube there is the barium. So it is a complex structure, and this type of structure is when there is again two types of different cations, and this structure can form. So as we have done before with other materials, here it is also possible to compute the theoretical density of crystalline ceramic materials from a unit cell data. And here is the equation for the density. And you see N prime. N prime is the number of formula units within the unit cell. Na is Avogadro's number, volume of the unit cell here. Sum of AC is the sum of atomic weights of all cations in formula unit, and sum up of AA is the sum of atomic weights of all anions in formula unit. Let me see. Let's do an example here. So let's look at this let's calculate this for sodium chloride. And N prime was the number of number of sodium chloride units per unit cell. So we're gonna take a look at a sodium chloride structure. Let's go back. Okay. You can actually, from the knowledge that sodium chloride forms an FCC lattice, you can actually know this number is 4. If you don't, you can calculate it yourself. So take a look at the green. Green ones are the chlorine, and the blue ones are sodium. So let's calculate the green ones. So they're at the corners 8, and it means just 1 is in the unit cell. and plus 4, right? 4 chlorine in the unit cell. So because these are 1, 2, 3, 4, 5, 6, 7, 8 at the corners, only 1/8 times of that is in the unit cell. That makes 1. And then 1, 2, 3, 4, 5, 6, and 6 meaning 6 times 1/2 is 3. Okay, so for this one. And then you do the same for the sodium. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 1/4, because 1/4 is shared for the edges. So that makes 3, and there is 1 at the center. So 3 plus 1, 4. So 4 sodium, 4 chlorine makes sodium chloride. How many of these? 4 of these, right? 4 of the sodium chloride. So that's why how many formulas per unit cell? 4. So we go back now here. All right. And we figured this one is 4. So we are calculating for sodium chloride. And now sum of atomic weights of all cations in the formula. So in the formula there is sodium. So what for sodium it is 22.99 gram per mole. So this is that. And for the anion chlorine it is 35.45 gram per mole. So in order to get so we know this one, that one, this one we know. We need to get what is the volume of the unit cell, which is AQ, right? So what is A in terms of the ionic radii? So if you actually look at one side of that cube, this is how the atoms fit, okay? So this is A, remember. This is the unit cell of sodium chloride. So here is how atoms fit. So this is chlorine. These are sodium, chlorine, and sodium here. Okay, so if you take a look at it, the A is equal to here this, let me choose another color, this plus that plus this. So therefore A is equal to and of course based on that R's are given to you. What is the ionic radii of sodium and chlorine? These will be given to you. It is this one is 0.102, this one is nanometer, this one is 0.181 nanometer. So based on that you plug it in and you get A cubed as a volume. So plug in the A cubed, the Avogadro's number, and atomic weights, okay, and prime is 4, and the density that you should get, and make sure you are correct with the units, okay. And this example is actually in your book, and the density should be 2.16 gram per centimeter cubed. So therefore convert nanometers to centimeters before putting them into the equation. Okay, that's it. Okay. So remember, ceramics are like oxides, silicates, nitrites. So we have seen oxides, some chlorides, and now there is the silicates. Okay, these are like composed of silicon and oxygen. These are the two most abundant elements in Earth's crust. This silicates the compounds of silicon and oxygen. Rather than describing as unit cells, it is more convenient to use the arrangements of the tetrahedron. So this tetrahedron is the building unit. As you see the tetrahedron here, the corners are the oxygen anion, and in the middle of this oxygen anions there is the silicon tetrahedron. There is the silicon, as you can see, cation. Okay, so there is the tetrahedrons I'm drawing for you so you see it. Okay, and as you see it. Okay, so in the middle there is the silicon and a silicon cation. So how these tetrahedrons arrange? They can arrange in a crystal structure in an order, or they can be amorphous. Amorphous means they might not have an arrangement at all. So that's being said, this silicon oxide can have different type of crystal structures depending on how these tetrahedrons are arranged. So that's why it is called polymorphic. So it can have different crystal structures. One of them is quartz. You guys might be familiar. And these structures have very high melting points because of the covalent bonds they have. It has very high temperatures, and it is actually the main component of the glass. So okay, so here is some silicates, and 1, 2, or 3 of the corner oxygen atoms of that silicon tetrahedron can be shared. So as you can see, this is the silicon tetrahedron here, and as you see, they can share one oxygen like that. Okay, like this. And then they can also share, let me see here, 3 corners here. Right there, like this. Okay, so based on that, they will have different structures, right? Different structures. And now these structures can have cations that are presented in the structure. And these cations like calcium, magnesium, aluminum cations. So they can have 2 roles. First, they compensate negative charges from the silicon tetrahedron so that charge neutrality is achieved. Second, these cations can also ionically bond to silicon tetrahedron. So this is actually, you see, a negatively charged anion. So it needs to preserve the charge neutrality. We need positively charged species, and they can be added structure to form the silicates. And this will to maintain charge neutrality, and this will also provide ionically bonding of different tetrahedrons coming together. So as I said, this tetrahedron is actually the basic unit of the glass, which is amorphous, but quartz is crystalline. So we have the same tetrahedron, which is silicon oxide, same tetrahedron. It can arrange in a crystal structure forming quartz, or it can arrange in an amorphous structure with the addition of sodium cation it can arrange into more amorphous configurations, which will form the glass. So these are actually called glass formers, forming an amorphous, inducing an amorphous structure. And fused silica is what we called no impurities added. Okay, when there is no impurities added, this is called fused silica. Impurities meaning the cations like sodium, calcium. So when you don't have these sodium and calcium or other cations present in the structure, but you still have an amorphous structure, that is fused silica. If you add these, you are forming different types of glasses, because there are different forms of types of glasses exist depending on actually what type of cations you are adding into the structure, depending on the composition. So a two-dimensional sheet or layered structure can also be produced by sharing of 3 oxygen ions in each of the tetrahedra. 1, 2, 3, right? Or 1, 2, 3. All right. For this overall structure, the repeating unit formula is presented by 2 silicon and 5 oxygen. It comes from here. So 2 silicon and 5 oxygen. So this is the repeating unit. So this unbounded oxygens projecting out of the plane of the page, as you see, these are having the net negative charge, and we need to establish electroneutrality. So we need another planar sheet of structure having excess of cations, which bond to these bonded oxygen atoms from this structural sheet. So therefore you will need another sheet of a ceramic structure where you have excess of cations, which will basically provide a neutrality when interact with these negatively charged sheets. So those are gonna be usually aluminosilicate structures, and it's a highly complex structure. If you are interested, it's a clay structure. You can take a look at it in your book. But the ceramics are, compared to metals and polymers, they are rather complex structures. Okay, here it is shown to us where we have this layer here. Negatively charged is compensated with a positively charged aluminum hydroxide layer, and this is forming kaolinite clay, and they are loosely bound to one another by van der Waals forces. So similar to silicon, there is carbon. Carbon is has a very diverse structure. As silicon, carbons can arrange in different configurations, and it will give us different type of structures. For example, diamond is a form of carbon. So carbon in that case bonded in a tetrahedron configuration again, as you can see. Okay, and this type of bonding of carbon will provide us a diamond structure, and diamond is known as the hardest material that is available to us. It has also very high thermal conductivity. It doesn't have a good electrical conductivity, but it has a high thermal conductivity.
So if it's made of single crystals, these are the diamond gemstones. And if there is polycrystalline, there are small crystals. These materials, diamond is very hard. That's why it is used as the cutting and grinding purposes to grind other materials, because it's very hard. So can be diamond thin films, which are used as hard surface coatings, used for cutting tools and medical devices. Another form of carbon is graphite, and graphite is, as you can see, a layered structure. It is you can see parallel hexagonal arrays of carbon atoms like this. So these are hexagonal arrays of carbon atoms forming one layer, another layer, and another layer. So these layers are bonded to each other with weak van der Waals forces. That is the reason this graphite is a very good lubricant, because the layers of the graphite can slide easily over each other. Remember, because the van der Waals forces are weak and it is easily broken. Now let's take a look at what type of defects can exist in ceramics. As it is possible with metals, both vacancies and interstitial sites are possible. But you need to keep in mind there is two types of ions in the ceramic materials. So defect can be one of these kinds, or both of them. But the anion is relatively large compared to cation. So the cations are the ones then forming the interstitial defects. So vacancies can exist for both cations and anions. When it comes to interstitials, since cations are smaller, it is possible more for cations. Interstitial are not normally observed for anions because, as we said, anions are relatively large compared to the interstitial sites. And you can see where these cation defects are forming. Here extra, it fits inside, and there's cation vacancy, and there's anion vacancy. Okay, the red atoms are missing, the anions bigger ones. The cation is the blue one. So there are other defects we call Frankel and Schottky defects. So Frankel defect is a cation vacancy, cation interstitial pair. So in order to understand these defects, you need to remember that the structure needs to preserve charge neutrality. So if there is a cation missing here, there has to be an anion missing there. So there is the Schottky defect is. So to preserve the charge neutrality, a paired or set of cation and anion vacancies. This way the structure can preserve the charge neutrality. If in the Frankel defect case, if there is a vacancy of the cation, therefore it has to show up somewhere else in order to preserve the charge neutrality, and it is somewhere here, right? So it still needs to be in the structure, but it goes to an interstitial site. This way the charge neutrality is still preserved. Remember the equilibrium concentration of vacancies, and it is the same as same equations can be used to calculate equilibrium concentration of defects in ceramic structures. And it was related to this exponential term, which had the Boltzmann constant temperature and then the activation energy. Alright, so as I said, in ceramics, the electroneutrality charge balance must be maintained even the impurity is present in the structure. So if you take a look at a substitutional cation impurity, why it forms. So you have sodium chloride structure here. The blue is the sodium cation, chloride is the green colored anion. And as you can see, without any impurities, the charge neutrality is preserved. So what happens, let's say, if you have a calcium cation impurity, then it has to be compensated by 2 sodium cations, right? So in this case, that is what happens if there is a sodium calcium impurity comes to your structure. So there is one vacancy here, cation vacancy. One charge is missing, and another charge is actually missing here because there is no sodium, but it is replaced by 2 sodium ions replaced by 1 calcium. So this can happen only if 1 calcium goes to impurity the sodium's place, replace 1 sodium. So 1 sodium is missing here and 1 sodium is missing there. So therefore presence of calcium replaces the 2 sodium. Okay, so this way the charge neutrality is preserved. So when it comes to substitutional anion impurity, without impurity, that is how sodium chloride looks like. If there is an oxygen missing, oxygen can be replaced with 2 chlorines. If there is an oxygen impurity in the system, in the sodium chloride system, if there is an oxygen impurity, it has to be compensated with 2 chlorine anions. So here the impurity comes, replaces the chlorine anion, one of them. So one of them is gone from here and the other gone from here. So then the oxygen replaces 2 chlorine in the structure. Okay. So at the end, the idea here, overall the charge neutrality has to be preserved. If there is a defect, if there is an impurity, the formation of defect is also rather complex compared to other structures.
So it is possible also to determine phase diagrams experimentally for ceramic systems. And when we say components here, when we say 2 components, it is not going to be the elements forming, okay? It is going to be the compounds forming it, such as magnesium oxide is the one component, and aluminum oxide is going to be the other component. So that is actually a 2-component phase diagram. There are several examples of these phase diagrams in your book. Here we take a look at magnesium oxide and alumina phase diagram. As you see, it is complex and difficult compared to metals. But SS means the solid solution here. So at certain amounts of the alumina, different types of solid solutions form and liquid form. Of course, liquid forms at very high temperatures, as you can see, about 2000 degrees C the liquids can form, and below these, according to this phase diagram, the solid solutions are forming in different amount of alumina and magnesium oxide, and there is another compound which is the magnesium aluminum oxide. And finally, let's take a look at the mechanical properties of ceramics. And we kind of know these ceramics are brittle
compared to metals. Think about a ceramic cup. When you just drop it, it breaks, shatters. Why is it? Because first, dislocations are difficult to move in ionic solids because of the strong bonding between the atoms. And remember, the deformation happens with the dislocation motion, and if there are no dislocations in a structure, it is difficult to deform that material. And I told you the only reason the metals can be deformed is because of the presence of dislocations. Well, in ceramics, dislocations are difficult to move. You need to keep applying a lot of forces to overcome and this force and to move the dislocations. So at that point, actually, you reach the strength level of the atomic bonds. And also they have a few slip systems. And it is not easy to that ions flow over each other. So resistance to motion of ions past one another. Therefore, the ceramics are very strong materials, very strong, stronger than metals, but they are also brittle, unlike metallic materials. So there is one technique to measure the mechanical properties of ceramics. Tension test is not preferred because they are brittle under tension, but under compression they are strong. And this is due to the fact that so if you take a look at if there is a crack present, and if we apply tension, this crack will have stress concentrations and will propagate. But if you do it under compression, it will not build up stress around the cracks. You are actually closing the crack, so it's not propagating. So under compression they are strong. Under tension they are weak. So there is this test called flexural tests, which is exposing the material to bending. So certain parts are in the compression, certain parts are under tension. So if you bend the part, this is gonna be under tension, right? This surface, but the inner surface will be under compression. So this test is rather preferred for measuring the mechanical properties of ceramics. Makes a better comparison in between different ceramic materials. So this test is called 3-point bend test because there are 3 points that the force is applied and bending the material, and then you are measuring the strength up until the strain up until the fracture. We know at room temperature the ceramics are showing elastic behavior, meaning they don't have any plastic deformation and they fail with brittle fracture. So as you can see, as a force versus deflection being this. So if this much bending happened, this is the deflection. Okay, so deflection is the amount of strain, you can think about it. And of course, as you can see, it shows a linear behavior with force versus the deflection. And this is of course how we measure the elastic modulus. Okay, so based on that, from the slope, the elastic modulus is calculated. Well, the bending modulus will depend on what type of cross-sectional you have. So based on that, there is another parameter here that you need to multiply to get the bending modulus, because think about bending, different types of shapes are different, right? You need to apply different forces. When you're trying to bend a circular cross-section, it's going to be different than some rectangular or square cross-section. Therefore, this shape factor comes in calculation of the bending stiffness, and therefore this factor has to be also included in the calculations, in the equations. Similar to that, there is also strength can be measured, and these are flexural strengths, bending strengths, and these strengths will require the calculation of bending moment and how far you are away from the center, which is called the neutral axis, because there is compression and tension in between somewhere. There is nothing, and that is called neutral axis. And based on that information, the moment and the neutral axis distance and the moment of inertia, this is based on the cross section, as I said, because depending on the cross section, the force, so the stress levels will be different. So all these parameters are included when we are calculating the strength, and that is where these equations come from. And you can find more information in your book, but not more than this is necessary. I'm not going to ask derivations of these equations or anything. So just to know, the flexural test is done to measure the strength of ceramics, and there are equations to calculate the bending modulus and bending strength. And this is how we make comparison between different type of ceramic materials, and this gives us the best data to be able to calculate the strength of ceramic brittle materials. So as you can see, we are given typical values for different types of ceramics. Here we are given silicon nitride, silicon carbide, aluminum oxide, and glass, and how their bending strength and bending modulus is different. So silicon nitride has the best flexural strength, and has the best modulus comes here for aluminum oxide. So in summary, what we have learned is we learned about ceramics. We learned they are rather complex structures. They can show ionic and covalent bonding, and they need to always maintain charge neutrality, and you need to keep in mind that when try to understanding the formation of defects. And the cation to anion radii ratios will determine what type of a structure the ceramic will have. And imperfections can be similar to we have seen in metals, like vacancies, interstitials, and there are also other ionic defects like Frankel-Schottky defects. There can be impurities, substitutional, interstitial. So the key here is to maintain the charge neutrality. And mechanical properties of ceramics are measured with flexural tests, and there is the elastic modulus can be calculated, and there is the flexural strength can be calculated. That's it. So next we're going to learn about applications and processing of ceramics.